welcome back. Today's goal of this lecture is, today I will see limit continuity of functional several variable by sequentially. In my previous video, I had seen limit continuity by epsilon delta definition and also sequentially, but I have proved every example by epsilon delta definition. But today I will do our all example by sequentially. I will do today how limit continuity is proved by sequentially, means by sequence. At first, just as a review, just recall in my previous video I had seen, if f be a function from U where U is the subset of Rn to Rm and x not considered this belongs to U, then f is continuous at the point x naught if for epsilon given epsilon greater than 0 there exists delta greater than 0 so that y belongs to U. Norm of x naught minus y less than delta imply norm of fx naught minus f of y less than epsilon. And in metric space this definition is as a distance function, and sequentially this is equivalent to, I had seen in my previous video, if xn be a sequence which is contained in the subset U where U is the subset of Rn and f be a function from U to Rm where U is the subset of Rn, xn tends to x naught imply if f is continuous then always f of xn tends to f of x naught, and xn tends to x naught means since here the multivariable calculus, so consider this is be the U which is subset of Rn, this is the open set which is subset of Rn, and xn tends to x naught means the sequence xn at some point tends to x naught mean in real variable for n greater than equal to capital N, the term of the sequence tends to the interval b of x naught minus delta, b of x naught plus delta. But here term of the sequence after some stage lies in the ball around x naught of radius delta. That means after some stage xn lies in this ball eventually. This is actually the difference between one variable and multivariable. And since here the multivariable calculus, so xn tends to x naught mean we can write this as norm of xn minus x naught tends to 0. That means that imply ball around x naught of radius delta which is denoted as b of x naught comma delta, and xn lies between this ball eventually. Actual idea, by sequentially we can define a function in multivariable calculus be continuous. And in my previous video I had seen one easy way to find in multivariable calculus a function be continuous. This is component wise method, and the method is f from U where U be the subset of Rn mapped to Rm and x belongs to U, then f of x1 comma x2 up to xn equal to f1 x1 x2 xn up to f of m x1 x2 xn, where each fi map from U to R where I equal to 1 to up to m, then f is continuous if and only if each fi is continuous. That means This is one easy way to find continuity. If each fi is continuous, then we can tell our function in functional separable variable always be continuous. Similarly, I will see in sequence also this is true. Let's continue our lecture, today's lecture. Today I will prove our all example by sequentially, because this idea not only prove, this idea is very conceptual for higher study. For higher study of functional several variable, this idea is very conceptual. But at first I will highly recommend you, if you don't see my previous video of functional several variable, at first see my previous video of functional several variable, then today's video would be so easy. Okay, let's continue our example. Prove continuity sequentially. At first I will see what is the meaning xn yn converges to ln. Here I have considered R2 just for short calculation. In multivariable calculus, this can be n variable. For short calculation, consider it only 2 variable. What do you mean xn yn converges to ln? In real line, we all of us know xn converges to the limit point L means there exists n which is greater than equal to capital N, such that absolute value of xn minus L strictly less than epsilon. This idea is for real line. Then what do you mean when in higher dimension? Here I have considered just as R2. Xn yn converges to Lm means actually xn yn converges to Lm. This condition is true if and only if xn converges to L, yn converges to M, and this condition is if and only if condition. At first see the proof, then you will understand in better way why this is true. At first, sequence xn yn converges to Lm means a sequence xn yn converges to Lm in R2 means if given epsilon greater than 0, there exists capital N such that for all n greater than equal to capital N. Here the sequence in R2, so here this distance is known. Here norm of xn minus Lm less than epsilon. Norm of xn yn minus Lm in R2. This is means square root of xn minus L whole square plus yn minus M whole square. And obviously this is always less than equal to absolute value of xn minus L. Obviously from this expression, this is actually same as this. Similarly, we can write this expression yn minus L always less than equal to square root of xn minus L whole square plus yn minus M whole square. And since this is less than epsilon, therefore for all n greater than equal to n, absolute value of xn minus L less than epsilon and yn minus L less than epsilon. That implies xn, the sequence xn goes to the limit while L, and the sequence yn, sorry here M not L, sequence yn goes to the limit point M. That means sequence xn yn goes to Lm means if you concentrate in the first coordinate, then xn goes to L, and if you concentrate in the second coordinate, then yn goes to M. Sorry, here for all n greater than equal to capital N. Sorry. Conversely, we have to prove if the sequence xn converges to L and yn converges to M, then is it true x and yn converges to Lm? For this, that means we have to prove given epsilon greater than 0, there exists a capital N such that for all n greater than equal to capital N, norm of xn comma yn minus Lm less than epsilon. We have to prove it. But given xn goes to the sequence xn goes to L and the sequence yn goes to M, from this expression we can write. So consider there exists n1 and n2 such that absolute value of xn minus L less than epsilon over 2 square root of 2, where for all n greater than equal to n1 and absolute value yn minus M less than epsilon over 2 square root of 2, where this n also greater than equal to n2. Here I have considered epsilon over 2 square root of 2, just our easy calculation. Then norm of xn yn minus Lm means obviously this is equal to absolute value of xn minus L whole square plus yn minus M whole square, and this is true for all n greater than equal to maximum of n1 comma n2, and I have got absolute value of xn minus L less than epsilon over 2 root 2. Therefore, this is less than square root of epsilon over 2 whole square 1 over 2. This is also plus 1 over 2. Just put the value. Then this is less than epsilon, and this is true for all n greater than equal to maximum of n1 comma n2. Okay. Therefore, I have got norm of xn yn minus Lm less than epsilon for all n greater than equal to maximum of n1 comma n2. Therefore, this implies the sequence xn yn goes to Lm. Okay. Therefore, xn yn goes to Lm means one side xn goes to L and yn goes to M. Conversely, xn goes to L, yn goes to M means xn yn goes to Lm. Have you understood this proof? Okay. Now, what is the continuity? For shortcut process, I have considered f from R2 to R and consider x0, y0 belongs to R2, and we all of us know in my previous video I have seen f is continuous at the point x0, y0 means bisequentially if we want to prove this means there exists a sequence xn, yn which converges to x0, y0, that imply if f is continuous, that imply f of xn, yn converges to f of x0, y0. As for example, at first I will see one easy question. First I will say just easy question, f of xy equal to x plus y. I will say this is continuous for all xy belongs to R2. For this, just consider one arbitrary point x0, y0 belongs to R2. I will prove this as sequentially. So, consider there exists a sequence xn, yn such that xn, yn goes to x0, y0. And if xn, yn goes to x0, y0, then that implies obviously xn goes to x0 and yn goes to y0. I will use the result of limit if xn goes to L and yn goes to M, then xn plus yn always goes to L plus m, that means x naught plus y naught, and xn plus yn means actually f of xn comma yn. Therefore I have got, and x naught plus y naught means f of x naught comma y naught. Therefore I have got f of xn yn goes to f of x naught y naught. Therefore xn yn goes to x naught y naught. That imply f of xn yn goes to f of x naught y naught. You can also prove this example by epsilon delta definition of continuity. We'll prove all question by sequential criteria. So I have proved this question by sequence, and for short calculation here I have considered R2 to R. We can write this as, for higher dimension, f from Rn cross Rn to Rn be given by f of x y equal to x plus y. Then similar to before, this function is continuous. This calculation you will understand in better way if you understand this equation. How we have solved this question by sequentially, then you can solve our given higher dimension equation easily if you understand this is in better way. Okay. Similarly, our next question, consider two continuous function f from R to R and g from R to R, which be a continuous function. Now define one new function capital F from R2 cross R such that capital F of xy equal to small fx times small gy and capital G of xy equal to fx small fx plus gy. Now I will prove these two functions, capital F and capital G, both are continuous function. Now I will try to prove capital F is a continuous function by sequentially, and I will leave G for my viewers. Solve the question how G is continuous function. If you understand how capital F is a continuous function, then you will understand in better way how capital G is a continuous function. So just pay attention. For this, since here capital F map from R2 to R, take a sequence xn yn which converges to x naught y naught. That imply obviously, this is if and only condition, xn converges to x naught and yn converges to y naught. Since given f and g are both continuous function, so xn converges to x naught, that imply fxn converges to fx naught and g of yn converges to g of y naught. Now from these two equations we can write f of xn times g of yn goes to f of x naught times g of y naught, and f of xn g of yn, this is actually capital F of xy, and f of x naught times g of y naught, this is from this equation we can write this is capital F of x naught y naught. Therefore I have got here x and yn. I have got x and yn converges to the point x naught y naught. That imply f of x and yn converges to f of x naught y naught. That means, that imply our given capital F is a continuous function which is mapped from R2 to R. Similarly, we can verify this is continuous. Please try to prove this question by sequentially. Our next question, similar to before, I will leave this type of question for just as an exercise. Just see the question. Same proof. But here the question for not R2. Here the question for Rn. The question is F from Rn to R and G from Rn to R. Both are continuous function. Then their product. Consider their product defined as the new function h, who is defined from Rn to R such that hx equal to fx times gx, where f and g are both continuous function. We have to prove this hx is continuous function. Try to answer. Second, if gx not equal to 0 for all x belongs to R and phi not belongs to range of y, then consider new function phi, who is defined from Rn to R such that phi of x equal to 1 over gx. Now try to prove this. This function phi is continuous function. Try to oneself, try to prove it oneself. Then you will understand this question in better way. Leave it for you just as an exercise. Please try to oneself. Now I will see some example of continuous function. These examples are very important but very conceptual. At first I will consider one mapping phi, who is from M to R such that phi of A equal to determinant of A. I will say this function phi is a continuous function. For continuity, consider one B, who is belongs to M to R, and one sequence Bk, who is converges to B. Then Bk would be such type AK, Bk, Ck, Dk. Who is converges to B means, since B belongs to M to R, this belongs to the matrix ABCD. And since Bk converges to B, from this expression we can tell AK goes to A, Bk goes to B, Ck goes to C, and Dk goes to D. We have to prove phi Bk goes to phi B. For this, obviously, phi Bk is determinant of Bk, and determinant of Bk is actually AK Dk minus Bk Ck. Okay? We have to prove phi Bk goes to phi B. And I have seen AK goes to A, so we can write this as A, Bk goes to B, Dk goes to D, here B, similar BC, and this is actually phi B. Therefore our proof has done. Phi Bk goes to phi B. Therefore, if Bk goes to B, that implies phi Bk goes to phi B. So, determinant function always be continuous function. Sorry, here one printing mistake. Here not Bk, here B. Sorry, very sorry. Now I will prove any nonlinear space is a continuous function. For this, consider a mapping f from x to r such that f of x equal to norm of x. And consider an arbitrary x belongs to x such that xn converges to x in the metric space x. Then f of xn would be norm of xn. And since xn converges to x in x, that means norm of xn always converges to norm of x. And norm of x is nothing but norm of x is f of x. Therefore, I have got xn converges to x, that implies f of xn converges to f of x. So, our given function is a continuous function. Okay? I hope my all viewers have understood this type of question, how we have to prove. Our next example is, consider D is a discrete metric space on the set X and rho be another metric space on the set X. Now determine all continuous function f from xd to x rho. At first, try to answer this question. In discrete metric space, every function is continuous. Why this is? At first try to answer. Now let's see the solution. In discrete metric space, any function be continuous function. Why this is? Because at first consider the function f from xd to x rho, which are continuous and which be the any function. That means every function in this metric space are continuous. If f from xd to x rho is any function, then for any x and for any sequence xn such that xn converges to x, that means in discrete metric space, we all of us know xn converges to x means xn exists eventually. That means there exists n naught belongs to natural number such that xn equal to x, and this is true for all n greater than equal to n naught. We all of us know this is. And from this expression we can write f of xn equal to f of x. This is also true for all n greater than equal to n naught. And from this expression we can write rho of f of xn comma f of x equal to 0. This is true for all n greater than equal to n naught. And for this expression, rho of f of xn comma f of x equal to 0 for all n greater than equal to n naught, we can write obviously f of xn converges to f of x. This is true for all n greater than equal to n naught. Okay? Therefore, xn converges to x imply f of xn converges to f of x for any function. So, in discrete metric space, any function be continuous. Our next question, f of xy equal to xy over x square plus y square. This is true when xy not equal to 0, 0 and 0 when xy equal to 0. Is this function is continuous at xy equal to 0, 0? For this, since we have to prove at the point xy equal to 0, 0, for this consider the part y equal to x and limit y goes to 0. Sorry, here y equal to x, here would be x goes to 0, x square over 2x square. This value would be half after putting the limit, and this value is not same as f of 0, 0. So, we can tell easily this function is not continuous function. But today I will try to prove all example by sequential criteria. For this, consider a sequence xn yn equal to such type 1 over n comma 1 over n. Then f of xn yn would be 1 over n square over 1 over n square plus 1 over n square. And this value would be 1 over n square over 2 over n square. And this is equal to just 1 over half. So, f of xn yn does not converges to f of 0, 0 because f of 0, 0 is half. So for this sequence, we can tell the function is not continuous. Here I have considered the sequence xn yn equal to 1 over n comma 1 over n because we have to check continuity at the point 0, 0. So I have checked this. So I have considered this sequence. For this considered sequence, I have got the value of this function is half. If we change the function such type, f of xy equal to this function, and at the point xy equal to 0, 0, the value is half. Now my question, is fxy is continuous at the point 0, 0? If you consider this sequence, then obviously this is true. But if we change the sequence x and yn equal to 1 over n comma 2 over n, obviously this sequence converges to 0, 0. But f of x and yn would be 1 over n square over 1 over n square plus 2 over n square. This value would be 1/3. Therefore, this is not equal to f of 0, 0. So for this sequence, this function also not continuous. Okay? I hope my all viewers have understood how we have to solve any continuity by sequential criteria. Today I will stop here. In my next video, I will discuss what is the differentiability in multivariable calculus. Actually, differentiability of multivariable calculus I have defined in my previous video. But just as a review, I will define this topic again. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.